Okay, so in the previous video, we learned that binary search is better than linear search in terms of runtime. So actually, it's in the name. Binary search has a log of n runtime, and linear search has a linear runtime. Now let's look into the auxiliary space complexity of binary search. So again, to get the auxiliary space complexity, we first start with the recursion tree for our function. So it's fairly straightforward for the binary search algorithm. So the index of key from 0 to n would call the index of key 0 to n over 2. And that would call the index of key from 0 to n over 4, etc., until we get to a point that we reach the function call key at from 0 to 1. So this is the assumption or the worst case assumption where the element we need to find is at index 0. So there will be still other cases wherein this can happen as well. So that would be at index n minus 1. And there will be several instances where this would be the case. But of course, this is the maximum number of calls that we expect. So what we need to know now is that the auxiliary space of the index function at each call, we expect it to be constant. So besides the recursive calls, we actually only needed one extra variable to store the midpoint. So what we just need to know now is the depth of our recursion tree, or how many levels do we expect this this recursion tree to have. So you can notice here that the at level 0, the n term is divided by 2 to the 0. And at our first level, the n term is divided by 2 to the 1. And at the second, at level 1, at level 2, we have n divided by 2 to the 2. So actually or the length of the partition can be determined by n over 2 to the level. Now, since our base case or the the condition to terminate our recursion is when our partition has a length approximately 1, we can equate that to this equation, or we can equate partition length to 1 and solve for the number of levels, or our depth, basically. So the depth will be the log of n, log base 2 of n. So now we have the depth, and since we have a constant space per function call using the general form of the auxiliary space complexity of a recursive function, we get that the memory space complexity of this particular implementation of binary search is log of n. So that actually means that our recursive binary search uses more space than linear search, which is just a constant, which just runs at a constant memory space complexity. So that leads us to the question here: is binary search better than linear search? So the answer is, I'm just reading this off our notebook. The answer depends on which resource you're willing to give up. So depending on the current computer you're using, you might have more memory, but you can't wait for too long. So of course you would want binary search. And then there will be cases where you won't have much memory at all, but you can wait for the result. So that means you can still implement linear search. But isn't binary search just isn't the memory space of binary search just because it's a recursive function? So what if we implement binary search without recursion? So that's absolutely possible. And it might even improve, and it should improve the performance of binary search in terms of memory. So if you're strictly going to use the implementation we have here, then we do have a trade-off between memory and running time. But if you can implement for yourself a iterative way or just using loops of binary search, then you could probably get a better trade-off, or actually no trade-off at all, at a better running time. Well, of course, the challenge there is actually implementing it. So recursion is one of the more straightforward ways to implement divide and conquer algorithms. So yeah, it's up to you if you're up to the challenge.